So, what's up? We are going to. Should I just zoom in a little bit more so you guys can see the code better? I don't know. Anyway, so we basically did the whole thing. So we got to this, and now we're trying to understand multi-head attention. So, hey, can you explain me multi-head attention in the context of the transformers architecture, again in simple terms? Is a key component in the transformers architecture. It allows the model to attend to different parts of the input sequence multiple times in parallel. So our input sequence now, it's basically this stuff here. That's our input sequence. The attention mechanism works by taking in three inputs: the query, the key, and the value. These inputs are linearly transformed using learnable weights, and then used to compute a weighted sum over the value matrix, where the weights are computed from the similarity function between the query and the key. Three inputs: query, key, and value. This is Q, this is this shit, this is this stuff. So this is query, key, and value. Okay. Okay, so these are essentially, D model. Are we sure it's the model? Because I'm assuming, okay, so this is linear transformed using learnable weights, and then used to compute the weighted sum over the value matrix, where the weights are computed from the similarity function between the query and the key. I guess query, okay, so I guess query is basically, I guess they are, okay, I think query and key will be the same. One day, they kind of represent. They represent, I think, each token. But why it's then demodel. So let's see. In multi-head attention, the input to each attention head is first linearly transformed separately. This allows each attention head to focus on different aspects of the input. The output of each attention head is then concatenated and linearly transformed. The use of multiple heads enables the model to capture attention at different levels of granularity and identify different relationships between the input tokens. The final output is a tensor of the same shape as the input value matrix, but represents a transformed version of the input where each token may contain information. So each token may contain information from multiple tokens in the input sequence. Okay, so this means the final output is of the same shape as our input IDs, right? IDs after position encoding. Yes, that's correct. In the provided code, the input tensor X is the positional encoding of the, and has the same shape as it, which is batch size max length D model. Exactly. Well, we don't have the batch size because that is the amount of inputs. We just have max length D model, and this is 1. The output tensor from the multi-head attention layer output also has the same shape as the input tensor X. That's X. Is it? Did we actually call it X? Ah, yes, it's X, exactly. X is what we have. Okay. So essentially, what we'll get at the end is that's pretty. So So what we're getting at the end is we're getting basically the same thing. So we have that input that's encoded, but now each input has additional information that essentially encodes similarities between other words, right? Whew, okay. Okay. You know, this means essentially that, like in our sentence, right? The quick brown fox jumps over the lazy dog. You know, let's say the token that represents lazy, at the end of all this process is gonna have encoded basically the word itself, the characters. Is gonna have in the encoding is gonna have also information about the position, right, in the sentence, and then it's gonna have information that relates it to relevant word to other relevant tokens. For example, probably, you know, the token dog, right? Interesting. Okay. Cool. So that kind of that's interesting. So we will just have that. I guess this yellow added norm is just probably normalization stuff. And then feed forward. But I don't, so we're just doing these right now. Positional encoding. And then the output embedding, shifted right. I have no idea what that is though. Masked multi-head attention, output probabilities. Oh, what are the output probabilities of the next? Is it like next character? I guess next word, next token, probably. Okay. But we're expecting to have the same shape, right? So, okay, so what are we doing here? So we're basically telling the model we're just giving it D model. That bothers me already, but we're not giving it max len. And it seems like that's supposed to have max len somehow, right? Or not. So we initialize the model, and it's making sure first that the dimensions are, the D model is divisible by number of heads. This is already, I'm not happy with this because, again, D model is basically the dimensions we use to represent each token. Okay, so can you explain me what D model is again? So each input token is a vector of length D model, exactly. So this means that, well, to my understanding then, it will make more sense if we're trying to split the attention into heads. We're doing this on like a max len, right? Shouldn't, so the problem is I'm curious, because if you're asking questions to Ghostwriter, like implying already like with a positive tone, I hope it's not biased to telling you know, yes, right? So the head splitting mechanism, the multi-head attention should split the the tensor by max len, right? Essentially, we need to basically take a look at and split the sentence in multiple sequences of tokens. Fucking Google Assistant. You probably didn't hear it, but it's just like I had the door open and it answered me. And it's just so dumb in comparison to Ghost Rider. So the multi-head dimension should split the tensor by max length and not demodel as it's currently in the code. Oh, it actually tells me no. Interesting. Okay. Okay. Maybe we're slicing it into dimensions. Yes. I know why it makes sense. We're slicing it from a dimensions perspective because, of course, because we want each head to encode information in a portion of that state vector. So if I represent each token with 9 or 10 elements, right? Or let's say 9 elements because it's easier. And then I say I want 3 heads, right? This means the first head is going to put information in the first 3 dimensions, the second head in the other 3 dimensions, and the third head in the other 3 dimensions. Okay. So each head essentially encodes data into a subset of the token dimensions. Correct? Yes. Awesome. Sorry, guys. So each head in the multi-head attention layer encodes information into a subset of the dimensions of the input token embeddings. The idea behind this approach is to allow the model to attend to different aspects of the input simultaneously by looking at different projections of the input tensor. Each head learns a separate set of weights that enables it to attend to a different part of the input. How is that so, though? That enables to attend to a different part of the input. So let's say I split that tensor like that, right? I'm still thinking 3D. It's easy enough because it's like, you can still think in 3 dimensions if I ignore the batch size. So, okay. So I split that, and what is it gonna do then? How is it gonna learn? How is it gonna learn different things though? I guess this is then. This is more about like how the actual processing looks like. Scaled attention, split heads, Q, K, V. Okay, so that's correct. So first, D model must be divisible by num heads. And what do we have here? So we have D model 10 num heads. We'll do two heads. Okay, so we'll do 2 heads. So we have 5 and 5. And then so self D model num heads. The depth is basically, of course, D model divided by num heads. So you have a depth of 5. So, and now this is okay, this is self-understandable. And then, okay, so now we're creating these matrices. So this is what I need to understand a bit more again. So can you, okay, so can you elaborate a bit more on what the Q, K, and V tensors are? So these are the query key value tensors. So in multi-head attention layer, we use the 3 separate learnable weight matrices to project the input tensor X into separate query, key, and value tensors. Okay, so so we have 3 things. So we take the input and we put it in, okay, in query, key, and value, whatever that means. Here's the equation that defines these projections. Okay, yeah, so essentially, but they're initialized randomly. Okay. They initialized randomly. But why demodel demodel? Why are they initialized randomly and with shape demodel demodel? Okay, the random initialization makes sense. Yeah, that makes sense. Sorry. Additionally, in the multi-head attention layer, since we want to attend over all dimensions of the input tensor, we need to project the input tensor into a space where attention can be computed. Therefore, we cannot simply use the original input tensor dimensions. And we project them to a higher dimensional space using... Oh, okay, that's getting now trickier. Okay, so this is just we're going somewhere else completely, right? So we're basically creating a separate space where we're projecting this stuff. Let's keep reading here. So each of these projected tensors has the shape. Okay, but I don't get it. So X is the input tensor and it has this shape. Okay, for us batch size is 1 so far. And these all are just, okay, so they are just matrices. Okay, they are just matrices of like demodel by demodel. And so if you do the multiplication, each of these projected tensors has preserves this shape. I don't know actually. Yeah, maybe. This is what we're doing. This is what we're doing here, right? So yes, so we're calling XXX. So we're taking the input and then just essentially doing that. All right, let's think about this for a second. So these are projections. So these are projections onto some just basically 3 random demodel by demodel spaces, right? So let's think about this. So essentially our input is just, we have, let's imagine it's just batch 1. So we have like 10 words. Each word has 10 dimensions of like information that represents it. So that's a high dimensional array, right? It's just a tensor essentially. And now what we're doing is we're projecting these on like 3 random spaces of like demodel by demodel. So why are we intuitively projecting? So what's the intuition behind the need to project the input onto 3 random subspaces. To attend to different parts of the input in parallel, while still allowing different subspaces to interact with each other. In the standard attention mechanism, we compute the attention score between a single query vector and the keys of all the other input vectors. However, in the multi-head attention layer, we use multiple projections of the input tensor, which we refer as to query key and value subspaces. By doing this, we enable the model to attend to different aspects of or features of the input by projecting them onto different subspaces. This increases the model's representational capacity and makes it more flexible. Because that's what's sometimes, I mean, that's what's definitely difficult to intuitively understand, right? So why are we doing this? Like, what's the intuition behind this mathematical operation here? So we have our representation, but then we're projecting it into 3 different spaces. I guess, you know, you have to think about this projection as, yeah, actually, of course. I mean, if you think about, it helps a bit to think about graphically a projection from a 3D vector to a 2D vector, right? So you can have like a 3D vector, and then you can project it into like multiple 2D spaces, right? Which essentially is what we have here. So I don't know if we don't have to go back into add that batch, because that's what we're doing. So we're taking a look at because here I only have no, that's 3, right? No, that's 3-dimensional. It's, well, it's 10 by 10. The shape. So you have essentially, you have a list of 10 elements, and each of these 10 elements kind of has 10 elements of depth, right? But essentially that's a 2D tensor, right? So I guess if we add the batch size, because the batch size then is multiple sentences is my assumption, because it would make sense, as in like why we're doing projection, because we're doing 3 random projections, basically to look at that information from 3 different angles, right? Like if you imagine like a 3D vector, you can project it in like many random 2D planes, right? And these projections basically tell you a partial story of these vector, right? So yeah, it's quite smart, because in essentially what you're doing is you're just making it more representable. I just don't know why they're called query key value though. Why are these projections called query p and value. Okay, so the query vectors are used to compute the dot product attention scores between the current position and all positions in the sequence. You know, the query vectors are used to ask a question about which positions are important to the current position. Similarly, the keys represent the positions being attended to. The out and values are the outputs. The keys and values are like the dictionary of information being indexed and retrieved. By breaking up the input tents into these separate projections, we enable the model to attend to different features of the input in different ways, which can be very helpful for capturing complex relationships between different parts of the input. That's true. So essentially what we're saying is, okay, so I guess we're doing it in two. So this is just going to be the output. I guess, right? So we're basically looking at two separate projections, and then we're trying to see what relationships are between these two projections. Basically, yeah. So basically, of course, by looking at like I guess the similarity between these two. I don't know if that similarity is something that makes sense. And why? But you're going like, you're essentially saying, I have this sentence that's got a bunch of tokens, right? A human just looks at the sentence and kind of, I guess, we don't pay attention to all the like huge amount of correlations or relationships that you might find between tokens or words. While what this system is doing this, is taking the input and then basically projecting it in like two different random subspaces, and then looking at how these projections relate to each other. Yeah. That is quite a mental stretch, to be honest. It's quite a mental stretch. Huh. D-model by D-model. I'm not so sure I understand why the specific shape is what's gonna make it work well. But let's see what's going on with these. So let's go step by step. Okay, so doing matrix multiplication between these, right? So and then we are calling this split heads. But let's first get into these. So let's just comment that out. I guess that's Python. I'll do what I did last time. Transform code. Comment aloud. Is that slower? Is that slower than replace selection? Is that slower than me doing it by hand? Who knows? Okay, so, and now we want, it's funny because like it becomes sometimes just easier to do like print the results. Yeah, that's what I want. I'm not even gonna read what else do you have there to tell me, bro. And then we want to see the shape as well. The shapes, please. Okay. Oh. Yeah. First of all, hopefully, I mean, yeah, that at least that shouldn't break, right? Let's run it. Boom, it broke. Why? Attention weights. I think that is. I think we should just, first of all, comment that out, just call these, and then comment that out. So that's for sure. Yeah, there you go. 10 by 10. What bothers me is the following. So let's just make sure that, for example, max length is 15. Okay, so that we have like longer sentences. So it indeed keeps the shape. It's just like it's matrix multiplication. Essentially, it's so rusty. I thought. So what is Mammal? What is Mammal doing? What is Mammal doing? By the way. So function returns the matrix product of two arrays, maybe 2D arrays. Okay, so it also accepts high dimension array. So n times m and m times p. So what's the relation of the output dimensions with regards to the input dimensions? Yeah, but I mean of the two matrices, right? So matrix multiplication. So, okay, so you're doing these times these. Yeah, okay, cool. So you essentially get the same. So, okay, so you get the shape of. You get the same amount of. Boom. Ah, okay. That's why. Okay, so it doesn't matter. This dimension doesn't matter. I'm just doing it in my head. What matters is this dimension, because you want to have, essentially what you're doing is you want to keep max length, right? So that's max length. Max length is the rows in here. If it's just thinking about one sentence, max length is the rows. It's the maximum amount of tokens in a sentence, and then this is D model. And so, of course, you want, this must be D model because you want to be able to multiply by this, and then this, it's just, it can be anything, it doesn't matter. This dimension here doesn't matter, like how many columns this one has. So I think it's just a convention. So, okay, I got it. Okay, so what do we, okay, so now we have basically 15, that's the amount of words, and then 10, that's the model. So we have these matrices in here. Okay, that's all cool. And let's just understand it's you know, these are, we're talking about just give me a second, guys. Give me a second, guys. So cool. I think I just have a couple of minutes, but it's good progress, definitely good progress. So okay, so we've done projections. So we're projecting. Let me add just here as a note, right? So we're projecting into subspaces in order to basically learn correlations, I would say, right? And of course, that this is something that, you know, that randomness here is what gives you that. Pretty cool. So the next step is splitting the heads. Some code. Comment, please. Okay, so we're splitting the heads. What does the split head function do? And we're just going to do 3 more minutes. The split head function takes a tensor, right? So it takes each of these, and what it does is, look, batch size. That's the problem. We are going to comment these out for now. We're just working with batch 1, so. So we're reshaping X. I think that's what we're doing is just this. That's what I would do. So we're reshaping. Whoa. I don't know. Are we? Split heads. How does reshape work? Isn't that supposed to return? What is num heads even? That is num heads is here. Okay. Okay, this is okay. I need to understand a bit better what's going on here. So that's for the next video, definitely splitting the heads. So we're okay. So we're projecting into. So we've done today the projection, and then this is the next step is understanding how the head splitting works. But I guess because I don't think that's correct. But I guess what's got to happen is each of these dimensions is basically. It's basically split into, like in our case, two tensors, like yeah, because. But then the splitting is just for parallelization, right? I think the splitting is the head splitting just for. Is the head splitting just to enable parallelization, assuming the GPU can do that? Yes. Okay. Okay. So that's just purely for parallelization. Okay. Yeah, that makes sense. It's just parallelization because then I guess it's different operations you're doing. So you're not multiplying a huge matrix. You're multiplying 2, and then the GPU can probably parallelize some of these if it's smart enough. Okay, so far so good. I think today's been quite a good learning. So let's just try to rephrase this once more. So essentially, what the multi-head attention is doing, and it's just multi-head because of we want to parallelize stuff. But the attention mechanism, what it's doing is essentially taking your input, projecting it into subspaces, and then basically taking a look at the relationship between these subspaces. This is a mechanism. I guess this is a way of working that tries to essentially capture relationships that might not be too obvious, right? Instead of hard coding relationships, like saying, oh, there's an adjective here, there's a noun here, this noun and adjective are probably related. You're like, no, fuck that. Like, we'll just take a math approach and just just do projections and look at relationships, right? So Pretty cool. Pretty cool. The question is going to be whether that relationship, if this is going to be with like the dot product or something like that, you know, what's the meaning of these, right? So let's see. See you next time.